So, last class I have discussed about the seismic refraction test and I discussed about the 2-layer case. Now, this lecture I will first discuss about the 3-layer case, then I will solve one particular problem. So, now this seismic refraction test, as I was discussing, that there will be a critical distance. So, if I put geophone within the distance xc1, then the direct ray will reach first. If I put the geophone within the xc1 and xc2, the refracted rays passing through the interface of first and second layer will reach first, and if I put a geophone beyond xc2, then the refracted rays passing through the interface between second and third layer will reach first. And this is the expression and the two methodologies by which we can determine the thickness of the first layer. Now, I will discuss about the 3-layer case. So, the 3-layer case, the similar type of expression I will give. So, T d is equal to x by V p 1, this is expression 1, and T r 1 is equal to x V p 2 x B p 2 plus 2 h 1 root over 1 by V p 1 square 1 by V p 2 square. So, this is the T r 1, that means the refracted rays travelling through the interface of first and second layer. Now, for the second and third layer refracted rays T r 2, that expression is x V p 3 plus 2 h 1 root over 1 by V p 1 square, then 1 by V p 3 square, then plus 2 h 2 root over 1 by V p 2 square minus 1 by V p 3 square. Okay. So, similar to the similar to the first case or 2-layer case, in the 3-layer case also we have to extend this because this line, and then this will give us T 0 T r 0 2, okay, T r 0 2. Now, if I put this value, the T r 0 2 here, so I will get, this is the T r 0 2 x equal to 0. So, I will get 2 h 1 root over, this is at x equal to 0. So, h 1 by v 1 square V p 1 square 1 by V p 3 square plus 2 h 2 root over 1 by V p 2 square 1 by V p 3 square. So, here I have already discussed how I will get the h 1. So, h 1 is expression is given, that I am giving only in terms of time. So, T r 0 1 divided by 2 V p 1 V p 2. So, root over V p 2 square by V p 1 square. So, this is the expression of h 1. So, by using V p 1, V p 2, V p 3, I will get from the slope of the curve, then I will get the h 1 from this expression, and T 0 1 T r 0 1 I will get from the curve. This is so I will get the h 1, all the velocities, the only unknown is h 2. So, I will get the thickness of the second layer also. The h 2 is in that way half T r 0 2 2 h 1 root over V p 3 square by V p 1 square divided by V p 3 by V p 1, then V p 2 Vp3 divided by root over Vp3 square by Vp2 square. So, this is the expression of H1 and H2, and I have discussed how I will get the H1 and H2. Okay. So, now I will solve one example problem that this is the example problem that we have done a refraction test at a site, and these are the distance from source to the geophone or the receiver, and this distance from the source, and this is the time of first arrival of wave. Then the first arrival of the wave, and that is in millisecond, and we have determined the thickness of the layers and the wave velocity. Okay, so I am putting I have drawn the graph here. So, I plot all the values in a Excel sheet, and then this is the distance x, and this is the TR, or this is the t time. So, from this graph I can see that this is the one slope, okay, and this is another slope, and this is another slope. So, I plotted all the points corresponding to x and t, because I know that this is the time and the distance. So, this time and distance are plotted in this graph, and this time is the first arrival time of the wave. So, I will get 3 slopes, that means the 3 layer case. So, it is a 3 layer case, and this will give us the Vp1, the slope of this state portion will give 1 by Vp1, this is 1 by Vp2, this is 1 by Vp3. So, from here I can write that Vp1 is coming out to be 500 meter per second, then Vp2 is coming out to be 1429 meter per second, and Vp3 is 3663 meter per second. Now, if I extend this line, and this one also, if I extend this line, I will get this value. This is TR01, this is TR02. Now, TR01 from the plot, it is 10 and it is in millisecond. So, in second I can write 10 into 10 to the power minus second, and TR02 it is 20 millisecond, this is 20. So, this is 20 into 10 to the power 3 second. Okay, so, now if I put, I know the velocity, if I put the H1, so H1 expression I know this is TR01 divided by 2 Vp1 Vp2 divided by Vp2 square minus Vp1 square. So, if I put these values, that means 10 into 10 to the power minus 3 divided by 2, then 500 into 1429, then root over 1429 square minus 500 square. So, I will get the thickness 2.7 meter. Similarly, for the H2, the expression is given, that is half into TR02 minus 2H1 root over Vp3 square by Vp1 square divided by Vp1 Vp3, then Vp2 Vp3 divided by root over Vp3 square by Vp2 square. So, if I know all these values, I know H1 also, if I put this value, I will get 7.22 meter. So, this way I can determine the thickness of the layer as well as the velocity of the different soil layer. Now, this velocity we can use for soil properties calculation, because these velocities are used for soil properties calculation. Now, we can calculate the shear modulus. The shear modulus is the rho Va square, and this is the Vp is the bulk modulus 4 by 3 G by rho. Now, what is Vs? What is the Vp? Now, this Vp is the velocity of the primary wave, and Vs is the velocity of the shear wave. So, these are the all body waves that will generate during the impact. So, the Vp is the velocity of the primary wave, and the Vs is the velocity of the shear wave. Okay. Now, this depending upon how you are generating the wave, you can generate Vs or Vp. So, now which wave you are generating? Suppose if you are generating Vs, then you will measure the velocity of the shear wave. And because I have derived all the equation by considering Vp, velocity of the your primary wave, but you can generate the shear wave also. If you generate the shear wave, then you will measure the velocity of the shear wave or velocity of the P wave or the primary wave. Okay, so that means and then if you are using the velocity of the shear wave, then you know the velocity of the wave, rho is the density of the soil, then you can determine the shear modulus. And if you know the velocity of the P wave, and then you can determine the bulk modulus of the soil also. Okay. So, but as I mentioned, in the refraction wave, it will give you the proper result if the velocity of the third layer is greater than the velocity of the second layer is greater than the velocity of the first layer. Okay. And most of the cases, this is the normal trend of the soil velocity. That means your density of the soil increases as depth increases because of the overburden. But sometimes if it is not the case, that means the density is not increasing with depth, or there is a very soft layer is within too dense layer. In such case, this refraction wave will not give you the proper result. So, in such case, you have to go for the seismic cross-hole survey, where you have to construct a borehole, and then we put the source inside the borehole, and then another borehole we put the receiver. We know the distance and we measure the travel time, then we will get the velocity. But with the previous test, that means the refraction test, it is a very time requirement is less, because where borehole we no need to construct the borehole. But in the seismic cross-hole survey, we have to go for the borehole, so it will take more time. So, here we can identify the change of the layer also, as we are going for the borehole. So, we have the borehole data and we have the soil profile we can identify, and at required point we can measure the velocity also, but it is time consuming. But sometimes a single borehole is also used. In that case, the source, either source or receiver is placed within the borehole, or the receiver or source is placed at the ground surface. Now, if the receiver is placed at the ground surface and source is at the within the borehole below the ground surface, then this is called seismic off-hole survey. And if the receiver is below the ground surface within the borehole and the source is at the ground surface, then it is called seismic downhole survey or downhole test. So, that means either you go for the seismic crosshole survey or seismic uphole survey or seismic downhole survey. Now, the this is the you can go for the 3 borehole case also, that means source and 2 receivers. So, here you can the one borehole there is a possibility of the error maybe more. So, that we can reduce also, and then we will get the soil property. Now, the last type of seismic refraction is geophysical exploration is the electrical resistivity survey. So, in this electrical resistivity survey, we basically pass the current through the soil, and then we measure the voltage drop, and then finally, based on that we measure the resistivity of the soil. Now, this resistivity, when you get the resistivity of the soil, and from this chart also I can get the different range of the resistivity for different soil. So, for sand, clay sand, gravel. So, these are the different range. So, I will get from this chart I can identify which type of soil it is based on the resistivity value that I will obtain. In addition to that, I can determine the thickness of each layer also. Suppose for homogeneous soil, what we will do for homogeneous soil, in all the cases the 4 electrodes are used. These 4 electrodes, this is 1, 2, 3, 4, and they are driven into the soil at the ground surface, and the outer 2 electrodes are used to send the electrical current, and the inner 2 electrodes are used to measure the voltage drop. Okay? And by this expression, I can calculate the resistivity rho by this expression. This is 2 pi d V by I. So, I is the current and V is the voltage drop. Okay. And d is the distance between the electrodes. So, these distances are generally equal. So, that means these electrodes are equally spaced, and this distance is d. So, for the homogeneous case, we know what is the resistivity, and we will get the value. So, we will get the pass the current, and then we will measure the voltage drop, and then by using this equation we will get the resistivity of the soil, and by using this chart I can identify which type of soil it is. But if it is a layered soil, then also we can measure the resistivity for each layer, and then and the thickness of the layer. In such case, what we do that we change this distance between the electrodes. Okay. So, we change them and we take the measurement for different d value. Okay. So, we measure the this resistivity for different d value, and then I will put them in this way. So, I will plot them. So, this is the x axis is the d is the different distance, and y axis is the summation of the resistivity, the summation of the rho. So, this is the d1 and then the resistivity, and next one d2 and the summation of the resistivity. Now, every time you have to sum the resistivity, and then I will get this type of plot, and then the slope of each plot will give us the resistivity for each layer, and where the slope is changing, that distance from the origin will along the distance axis will give us the thickness of the layer. Okay. So, this way we can determine the different soil properties as or the resistivity of the soil, and then different type of soil and the thickness of the soil layer. So, that means we can perform it for homogeneous soil as well as the layered soil. So, this way I have covered the soil exploration part. So, I have covered almost the major or the important tests, that in situ tests, those are conducted in the site to determine the different soil properties. So, some are directly we can determine the soil properties, in some case we have to measure the something else, then we can correlate those things with the soil properties, those are required for design purpose, and sometimes we can identify the type of soil also by using this type of tests. So, in the next class I will start the design part, that means the shallow foundation part, how I can use these soil properties that we have measured or we measure from the soil exploration, then how we can use them to design the foundation. So, initial part for I will discuss the shallow foundation, then I will go for the deep foundation. So, in the next class I will start the bearing capacity of the shallow foundation. Thank you.